exposure, man.
Yeah, that's crazy.
Hi, everyone. We build robots but can't use computers.
Is there any way to?
Damn, we could get it closer, maybe, and the exposure will be different. Yeah.
Oh, okay.
Okay, that's not terrible. Turn that light off. All right, well, we can do that. And then I'll be this dark, ominous figure.
Yeah,
I'll just stand in front of it like this.
yeah, that looks good.
How about this?
Now live. Okay.
And it shows it's live.
Yeah.
Cool. Are we good to go?
Yeah, let's go.
Wow, we did it, guys. We did it. Okay. Welcome, Internet, to Trial by Fire. Okay, so my name is Chuck Sullivan. I'm going to give a talk today. So this is a really long title, Comprehensive and Modular Robotic Control Framework for Modelless Control Law Development Using Reinforcement Learning for Self-Robots. I built a squishy robot. It taught itself how to learn. That's essentially what that is. So I'm going to go, it'll be a brief explanation of what soft robotics is, what reinforcement learning is, kind of going through the basics of it, and then we'll talk about what I did and how I got a robot to learn on its own. So a little background about me, because what's the point of giving a talk if you can't talk about yourself? So I got my bachelor's degree in mechanical engineering at the University of Nebraska. Through that process, I worked as a machinist. I loved building things, but I got tired of giving them to other people to program. So I went and got a master's degree in electrical and computer engineering at the University of Texas, El Paso. They don't really make robot degrees, but I wanted to do robotics. And so I just kind of made my own by getting 2 different degrees. Through school, I had internships at different NASA centers. So I worked at NASA Goddard Space Flight Center, got to work on a sounding rocket payload throughout the year that we actually got. I machined 90% of the parts, designed them, and we actually got to launch that, and it went up into space and came back down.
Mm-hmm.
Friggin' cool. And I remember that night, I told my friend, we were on the beach after the launch, and I was like, yeah, like I could do this the rest of my life. And he was like, yeah, you could, like that's a career. And I was like, oh, shoot, you can do that. So through that, I ended up NASA Langley Research Center for a variety of internships doing hypersonics testing for materials for like leading edges of re-entry vehicles. Did E-beam additive manufacturing. So that's an electron beam welder hooked up to a CNC machine and 3D printing with it.
Wow.
I actually have examples of that at home if you want to see it.
So cool, yeah.
Yeah. And then I did a project called Assemblers, which is a series of hexapod Stewart platforms that you stack on top of each other and creates this like really strong worm-like robot. And you use that as a general purpose arm to assemble structures in space and on orbit.
Wow.
And then I did the home soft robotics study, which is what we're going to get into. That turned into my thesis. And that was just a look into soft robotics. Where do they fit in space applications? Can we use them for something like in-space assembly or exploring another planet? So that was all during school. My career is kind of during school, kind of not. You could count the internships. But I was a student machinist at the physics shop at my university in undergrad. Then I got a job as a machinist when I graduated. Ironically, I got a degree in mechanical engineering and got a job for $11 an hour. But super valuable. I was living at home at the time, so I felt rich. Through grad school, I was a TA for 3D modeling, FPGA design, and basic circuits classes. And then I was a researcher for the Keck Center for 3D Innovation down at UTEP. There, I actually have a patent for a novel way to embed wire into a 3D print in situ. And then after that, I graduated. I was a substitute teacher and taught snowboarding, which is probably the highlight of my career thus far. Loved it. And then now my current job, as of a year and a half ago, I moved to Albuquerque. I work at Redwire Space, so I'm a contractor at the Air Force Research Labs. I do space robotics work and building robotic testing facilities for space structures. Yeah, it's awesome. I can't put we submitted 2 patents for space robots like last week.
Okay.
I didn't want to put that on there, but
Why
I
not?
did want to mention it.
Wow.
So yeah, that's where I'm at. So let's go ahead and get into the talk. First thing we're going to do is talk about soft robotics. What are they? Why are they different? Why are they like a special class of robots? Some people have a lot of questions about them. Then we're going to talk about reinforcement learning, which is a branch of artificial intelligence. We'll get into the details of that, but it's basically a model-less way for a computer to learn something completely new. And then we're going to go into my framework design. So how do I take soft robots and reinforcement learning and combine them into one piece of hardware and software that can have a robot learn? And then I'll talk about how difficult it became. I was very naive. Someone showed me 5 lines of code and said, "This is AI." And I said, "Wow, that's easy." That was stupid.
Teachable machine.
Yeah, you're right.
I don't think we do.
And then because so this is my thesis. So because it's my thesis, we'll go into all the things I didn't want to do and just wanted to get the hell out of school. So soft robots. When you think about a robot, a lot of times you think of like iRobot or just an industrial robot to manufacture. But soft robots are any robot that's made out of a softer material. So a traditional like aluminum or steel robot has an elastic moduli in the materials 10 to the 9th, 10 to the 12th. There's softer materials like silicone, rubber. A lot of times cables are used instead of like rigid things. So a lot of the soft robotics are bio-inspired. So you can kind of see an octopus arm here. A lot of stuff is derived from the ocean because those are soft structures that are actuating and moving throughout a medium. And so this soft robotics is a fairly new field, and there's a lot of research being done in it because there's just nothing there. And so it's completely open. So you have novel methods of actuation available. So a lot of times shape memory alloys are being investigated, which are, you heat up a piece of metal and it has 2 states that it goes between, pneumatic and hydraulic. We'll focus today on pneumatic soft robots. Tendon actuated ones, so you have cables that are through a soft material, and when you pull on them, they generate a certain type of actuation as they decrease in size. And then this one right here, my laser works. I don't know if it
does. Yeah.
Yeah, but I don't know
Oh,
if
yeah.
the internet can see it. So this one right here is actually a photosensitive material embedded in a silicon substrate. And so you shine light on it in different patterns, and it can actually crawl across the table. Yeah.
That's so cool.
Yeah. This one right here, this is called a tensegrity robot. And so this is kind of that cable thing. This is a ball that can roll itself, but then come across a boulder and actually roll up on top of it. And yeah. So does that satisfy your question? What is
Thank you very much.
Yeah. Perfect. So all of this work came out of the HOME program, which stands for Highly Organized Multi-Agent Enclosures, which is my mentor at NASA when I had my first job, or when my first day for this internship in particular. I came in and was like, "What am I doing?" And he's like, "Soft robots, space." And I was like, "Cool, what does that mean?" He's like, "I don't know, figure it out." So we came up with this idea of like four things that soft robots need to be able to demonstrate to be useful in a space environment: mobility, generating a complex shape or changing shape, joining together, and then rigidization. Right, that's the 4th one. So this is a robot. These are 2 robots. This is Sonic and Hedgehog, or no, Sonic and Tails. Sorry. And so what happens is you have these cables here that pull this robot together and form a burrito, and then along the outside of it are pneumatic chambers that you sequentially actuate, and it can actually roll across the table. And we were able to achieve a full rotation, so you could roll infinitely. And then these fingers here are just fingers that come together like this, and then the tips actuate, and so they cam in on each other, and they join together. I mean, it takes a lot to pull them apart. And then here we have, this is where my like wire embedding knowledge came into play. We have a low temperature, low melting temperature thermoplastic that you can, has nichrome wire in it, embedded in it. And so you can heat it up, make it soft, roll up, move across the table, unfold, and then it will cool down and rigidize in that new form.
How fast?
Not fast.
Okay.
It's got to cool down and it's embedded in silicone. So one of the reasons I came to the use of AI and control is because these systems are very soft. Silicone has 900% elongation capability and coming back to normal. So modeling, it's very difficult. I'm not a math guy. So like I didn't want to teach it how to move. That was going to be a really difficult problem. This is all of the control hardware to control all of the pneumatic actuators. There's an air compressor on here, under here, and we have 16 channels here that we can control manually. And then I did get it to the point where they had sensor feedback. So there was a PID controller hooked up to this, and you could reach certain states. That once again, that kind of showed how difficult it was to control these. That was a huge problem. So yeah, that led to.
Wait, sorry, you had sensor feedback that would know its position in the movement, or?
Yeah, so you'll kind of see the robot I built for my thesis is a version of that. So it's got a flex sensor in it that can tell what position it's in. So yeah, this was all built using pretty cheap off-the-shelf hardware. It's an Arduino Mega that's running and all.
Yeah.
So lessons learned from that. It was very limited in scope, automated operation, super difficult. A lot of overhead, right? So taking those boards and like fitting them onto a robot was going to be difficult. Accurate control was difficult, and then simulation was untenable. The tools don't exist for it right now. So we had a lot of plans for it: modularity, sensor feedback, evaluation techniques. What I really focused on was, those four things led into my thesis, right? We wanted to develop control law. We wanted to be able to do different robots with the same system. And then also figure out how to embed sensors in it to get feedback of the state of the system. So for my goal, it was to develop a comprehensive framework, so software and hardware, to operate a soft robot and then develop control law using AI, or a branch of AI called reinforcement learning. So let's talk about reinforcement learning. We know what soft robots are. We know what I'm trying to do. So reinforcement learning is based off of the concept of Markov states. And let me tell you up front right now, I am a hardware guy that likes to build things that got into AI. I am not an AI person that got into robots. So there are a couple things, such as this equation, that I know how to describe, but don't ask a lot of questions.
Is this the Bellman equation? Oh.
It is the Bellman equation. Wow, someone knows their stuff. It is the machine learning.
It was up there,
yeah.
You're the AI guy, right? That got into robots in the end.
Yeah. So the concept of reinforcement learning is you have an agent, and that agent is your robot, essentially. And it takes an action in a given environment. So there's the environment. So you take an action in an environment, and from that action, you have a reward. So you're trying to accomplish some task, right? And in this example, we're trying to optimize the speed or distance it can move across the table per given action, right? So you give a reward, and then you have a new state of the robot. And then you restart that cycle where you say, I have this new state. I'm going to tell the agent to take another action in the environment. And then we're going to evaluate how well it did. And then eventually what you do is you get this state to action mapping that maximizes this reward signal, right? And so you give the robot essentially points for trying to do something, and it will take those points and evaluate how well it's able to accomplish that task.
Does it make random decisions to modify?
We'll get into that. Oh, sorry. Yeah. So, math stuff, a different version of math stuff. So a good example of this, just to take us through it quickly, is we have this grid, right? And this is our agent, and it can move in 2 dimensions, and it's trying to get to this bottom grid, right? So we have our environment, we have our agent, we have our reward. And so here we have 10 points for reaching the reward state. And as an example, this is, you can give a negative reward to tell it actions to avoid.
Penalizes.
So we have a pretty neutral state here, neutral all around, negative, positive reward. So the beginning of this, we're going to kind of go through a history of reinforcement learning. There's been a lot of developments in it. But this is its most basic form, right? Is this Q table, which for a 2-dimensional representation, you have 24 states down here and you have 4 actions. And so it's just a big table of values that say, in a given state, which action gives you the best reward. And so what reinforcement learning does is it populates this table. So the way that works is the new value in the table is the sum of the old value, right? So you're building off of previous knowledge, times a learning rate, which is a parameter you can do that you learn quickly or slowly, and optimizing that parameter is very difficult. There's a lot of parameters. All of these parameters are choosable. And so my favorite research was actually, there was some guy that was using reinforcement learning to determine the parameters to best use reinforcement learning.
That's pretty good.
So you have your learning rate, and that's just a factor of how quickly you learn. You have your reward signal, which is how many points you get in each square. There's a discount factor. So basically, this is your new value. And so this discount factor is multiplied by the optimal future value. So what this term is doing is it's looking into the future, and it's saying, if I go from here to here, it kind of does a mapping of how quickly is that going to get here. So it kind of goes into the future and calculates, and that discount factor says basically how much do I look into the future, right? And then you have subtracted from the old value. I honestly don't remember what that is.
It's the difference, man.
So here's an example, and these are completely random numbers. But an example of a somewhat populated table. So let's say we're in state 0 right here. So state 0, we go to our table and we've done some learning. 1.2 is the highest reward. So we're going to go right. Okay, that puts us in state 1, if I remember correctly, right? And so here we're still going to go right. And in state 2, right, up doesn't get us anywhere because it's not possible. Left gets us back to our thing, and down and right, if we're over here, down and right are pretty much the same.
But that's cool.
Yeah.
Oops.
How many iterations you have to train?
Thousands.
Yeah.
Yeah, and that's on the low end.
Mhm.
That's only because I had to do it in my apartment as a physical robot. Simulations can do
Fast,
millions. Yeah.
Oh, you're doing physical robot. Okay.
Oh yeah, no.
Yeah.
Part of I left academia because all robotics in academia was simulation based. I don't think it's a real robot until you build it. So okay, so issues with Q learning, right? You have a finite state and action space, which means everything has to be really well defined. Poor scale performance, so populating all of those and finding things in between if you have a large action space. Our action space was 4 actions, up, down, left, right. But for a robot in 3-dimensional space, I mean, your action space is almost infinite, right? So as that space grows, your lookup tables become computationally expensive, not only to learn, but also to act. Once you develop your model, to look that all up, it's computationally expensive. And then you have a poor exploration policy. So the way that you choose the next action is there's a probability here that you're going to choose a greedy action and use the value that's highest in your table already, and a probability that you're going to choose a random action and explore the environment. But initially when reinforcement learning was starting, it was just a simple calculation of you had a probability of random or not. And then it was really low, so it didn't explore a lot. So The solutions in the deep learning community or in the reinforcement learning community were deep Q learning. Basically, you take this table and you replace it with a neural network, right? Lot less computationally expensive to go through a neural network. This gives you robust learning, so you don't have to explore every single action in space. You can learn things around it, and the neural network gives you that kind of fuzzy logic in between all those actions. And then it's scalable, right? A neural network can pack a lot of information just into those weights. So this is where we're going to get a little messy. So there's a lot of advances were made in reinforcement learning. Essentially, the biggest one was this actor-critic model, where you have two neural networks that are both learning together, right? And so the critic contains the state action mapping, that's like the replacement for the Q table, and the actor contains policy information. So that's basically saying like how well this state action mapping performs, and then helps you choose that. And so your Q value and states output is probably, yeah. So what this does is you have kind of short-term learning and long-term learning, right? It kind of separates those two things. And so the output of this is the probability of every possible action, right? And so that depends on a lot of parameters, like your learning rate, how much do you want to explore? A lot of different things go into choosing the probability for the next action. So one of the next big advancements is the deep deterministic policy gradient, which goes from a finite action space to a continuous action space, which is good for robotics because that's infinite. You have something called a replay memory buffer, ways to reduce noise from training. So you have 2 actors and critics, which gets you to 4 neural networks going on at once. And then you have a delayed update on copy. I've got a good diagram that shows all this in just a second, don't worry. But that essentially has another 2 neural networks, a total of 6 neural networks all being trained all at the same time. And these are delayed, so you're learning on the short term, and then you're using that learning data to populate even longer term memory policies. So then you do this, and then you do twin delayed deep deterministic policy, and basically you put 2 of them together. So you got all these neural networks all learning together, and they reduce overestimation and error. They just help out a lot. One of the big things too is noise addition and regularization. So in a given action, you're going to add noise to that, and that's going to get you to explore even more. So you may choose a greedy action that's already the best action, but if you add noise, you'll choose something slightly next to that action. And maybe that produces a larger reward, maybe it doesn't, but it helps populate that continuous space and finding everything in between the known actions. So this is it. You've got your active networks here. These are making decisions on what to do next. Your actor network here is choosing of those decisions which is best. You add noise. You make your next action in the environment. That comes back and is stored in what's called a replay buffer. So everything is stored here and not immediately updated. And then every once in a while, you grab random samples from this replay buffer, because if you've been going for hours and hours on end, there's still valuable information in the first hour that you moved, but you don't always want to do what's most recent, because then you can get stuck in what's called a local minimum. And so it might find a good reward policy, but you still want to explore everything, right? So these are used to sporadically populate these with data. And then after some amount of time, you take those and you merge them with your target networks. And so these end up being your final neural networks. And so by using random data from the past, short-term memory, and then this delayed update and merger into longer-term memory, you kind of get this balanced learning, right? Where you're exploring as much as you possibly can.
What's the signal that it's finished? It's found the solution.
So that is determined by reward. So your
Just
reward will be
maximum reward.
maximized.
Okay.
Yeah. Yeah. And you'll there's graphs of a successful learning later on. Did you have something?
Oh, is there weights on the replay buffer going back?
Not that I'm aware of, but probably. I think it takes random data here.
Right. Does it weigh it less from the distant
No,
past?
um,
Or is it-
No, and a lot of that's because, especially in early learning, you do take a bunch of random actions. So you populate this action reward space. And so that's still valuable information. And so you want to take samples from everything. Okay, so we got soft robots down. We kind of understand how reinforcement learning works. There will be quiz later.
You said it was a teacher.
That was a really good explanation. Yeah.
Oh, thank you. Yeah, the paper I wrote for this thesis, another reason I left academia, was they said it was too understandable. That was my review. Okay, so now we have our framework design and implementation. So bringing all of this together is a lot of tools, a lot of things that were not built from scratch, but basically pulling from what's already been done in the AI community, the robotics community, and assembling it in a way in which a robot can learn. So first thing is the libraries around reinforcement learning have actually become pretty mature. I haven't looked at it in 2 years. I graduated and said, fuck that.
Made for children.
So something in the RL community is that things move very quickly. Updates are happening a lot. There are thousands of papers published a year in it, and so like things might be a little bit different now. But OpenAI was the gold standard back then. So you can create an environment in OpenAI that is compatible with RL algorithms, and then the library called Stable Baselines is a reinforcement learning library. And what these allow you to do is you can make an environment, change it very quickly without having to change your reinforcement learning code. And then Stable Baselines allows you to use that same environment and quickly swap out different types of reinforcement learning algorithms. So the one that we converged on was the one I eventually used, but I could have used all the different advancements along the way to find out which algorithm worked best. So this is very much for reinforcement learning research and not necessarily for like implementation. But you can force anything you want. So the other thing is you have hardware, you have software, you have AI, you've got cameras monitoring the system, bunch of things going on that all need to come into the single environment and be able to communicate with each other and pass data back and forth. So robot operating system is built specifically for that. It's not an operating system. Do you not like Ross? I love it. It's so good. A lot of people hate
Too much
it.
overhead for me.
So ROS basically allows you to create individual nodes of all different kinds of things, whether it's serial connections, reinforcement learning, all that. We'll talk about the details of how I implemented it. And so these nodes can publish and subscribe to data, and ROS handles all of the data transfer between different things. And so it's widely used in the robotics community. There's a lot of tools out there. So like a couple of things I had to do, I would just download libraries for, and it would pretty much work out of the box, which saved me a lot of time and headache, I guess. So this is the general design of everything. And so we're going to go back to this concept of Markov states, right? We have our agent, it takes an action in an environment. We have a reward in a new state. And then we just keep cycling through that. And we keep updating our neural networks after we get our reward. So let's talk a little bit about this organization. So here, I'm very colorblind and these colors were chosen at random. So it's really hard to say like, look at this blue square. This big one, this is everything that's basically on the computer. So this is where our reinforcement learning environment lives. And then that communicates with the actual environment out here. So if we're talking about the action generated, our reinforcement learning process will generate the next action to complete for the robot. And so that gets transferred out to, it gets mapped to what the robot understands, gets sent out to the hardware. The hardware processes that, and then your actuation is your actual your action in the environment. Man, that's a lot of AC words. Okay, so coming back, that's our agent taking an action in the environment. So now we need to take information from the environment about the state of our robot. So our robot has some sensors on it, so it knows where it is in space or what it's doing. That's converted to hardware, that's sent over serial back into the computer, where then it's translated back into something that the reinforcement learning algorithm understands. So you have your robot state here. So you have your action, your state, and then your reward is done. So I use April tags, and I'll explain what that is in a little bit. But basically, you have a way to monitor how well your robot accomplished its task. And so you take that, you get that data, and you put it back into the computer, and you essentially take the data, figure out a reward, and then that reward is put into the reinforcement learning algorithm. And then here, there's a bunch of different things you have to do, because robots, they don't call it hardware because it's easy. It's one of my favorite things.
Easy way.
Yeah. So like I had to build a system that just like reset things every once in a while automatically because it just stopped working. And then another system that kind of understood the whole system and knew, like, could determine if it was currently completing an action or waiting, because we had to. So in simulation, when you're doing reinforcement learning, it just goes as fast as possible. But here we had to wait for a physical robot to move in space. So we had to wait till that was done to be able to calculate the reward properly. We had to finish the action first. So there's just things that I had to do to make sure that we weren't going too quickly. So
Wow.
one of the things that was very frustrating, but ultimately turned into one of the best parts of the thesis, is COVID happened right as I was gearing up to do my actual research.
Oh, you just got your thesis.
Yeah. Oh, yeah. I graduated December 2020. So this was my robot environment in a nice clean lab. It was on an optics table. I had a sick whiteboard. It was cool. So COVID happened, so I had to move everything into my apartment. So this is a card table with plywood nailed to the top of it. A gantry here that has a camera. I did have a cool whiteboard in my apartment. But I just love this because I'm very proud of my grad school studio apartment. I had 2 3D printers, a soldering station, my computer here, some gaming here. We'll see a video later, and it goes from light to dark because while I was filming, I was playing Halo 3, and I had to shut the blinds. So yeah, behind this is a bed and a very small kitchen, and this was my life for 6 months.
Wow.
Yeah, and so this was where the robot would move. A lot of things happened over here. We'll talk a little bit more about that in detail.
So you're doing all the computations on a local computer or in the cloud?
So I had a laptop here
Yeah.
and a USB cable that went, did it go up? Yeah, I think one of them went up above at some point, and then another one came down below over to this environment here.
So you're doing it all on the laptop was processing all that?
Well, so the beauty, so it is computationally expensive to run reinforcement learning and process all those neural networks. But when you're doing it and you're waiting 20 seconds for a robot to complete an action, it doesn't matter.
It doesn't matter as much.
Yeah. So I just did it off a standard, I think it was an i5. There was a GPU on there, but I don't know if it ever used it because it was Linux and the drivers suck. So yeah. So this is our robotic area.
Wow.
My least favorite part about this whole thesis is that this is a pixelated image. So sorry.
You can change that with AI.
Yeah.
I don't know anything about AI.
You can roast this up.
So if we go back to our concept of action, state, and reward, our action is here, and these are a couple of just pneumatic syringes bought off of Amazon that I hooked up to some stepper motors. And then I have a CNC controller running that. So our action is completed here, and those pneumatics are hooked up to my robot here. We'll go more in depth on how this thing works. And then we have our hardware here that determines the state and sends it back, but also receives an action and converts that action into a physical reality. We have a camera up here, very high-tech, $30 USB camera, monitoring our robot environment, which is here, right? So a couple things to note. These tags here, which you can't really see right here, but it's essentially a QR code. And from an image, these tags are designed, you can get position and orientation data off of this tag relative to the camera, right? And so what that does is it allows me to determine this robot's, I didn't care about a lot of the position or the orientation especially. I just cared about its XY position.
So I was expecting it to be gridded, but that's cool.
Yeah, so you can just do this. And so what I was trying to learn was I wanted this robot to optimally move across the table, to learn to move. So it had no knowledge of itself previously, didn't know anything, and it would experiment and learn. So yeah, here's a more detailed look at that. Just a bunch of 3D printed parts and some kits, this is what I was talking about. Moving back to my apartment was really helpful because before I was gonna do like pneumatic channels with like solenoids and stuff. And after I started doing this, I mean, this is a closed system. So I knew exactly how much air was pumping in here. It lasted a long time. It was really nice. So that's how I would move. So you had open loop control, but we had sensors embedded at the bottom of this. So you could determine the state. And then I just had like an open source Gerbil controller, which is a little hat for an Arduino that turns it into a CNC controller. Huh. And so I was literally taking the actuations and packaging them as G-code.
Mm-hmm.
So this is how, this is how it would work. So you have your reinforcement learning algorithm over here. It would generate actuation commands. I would have a script that would take those and map them to, so I did some calibration to find out like what was a 0% move and what was a 100% move. I'll talk a little bit more about that. But basically it packages it to, do I want to move 0 through 100%, and takes them over here to another script that packages them as G-code and sends them out over serial to the Arduino, and then you actually actuate out here. I used the coolant pin as a way to determine if an action was happening or not. So basically in the G-code, it would just say M8 or M9, which is coolant on or off. And so that would be read by another Arduino to say, if it was on, something's happening, don't update the algorithm. Then when it went from high to low, it would know an action was completed and know to continue. So here we have our state acquisition. So in our silicone robot, there are these SparkFun $10 flex sensors, right? And these are really meant for like kind of a binary flex sensing. They aren't super accurate or give you good information. They just change resistance based on flex. But where you flex it and how much, like, it's not very accurate. But that's fine, right? Because we have reinforcement learning to take care of that. We're populating neural networks. So it's finding all that fuzzy logic and basically compensating for our lack of ability to understand the robot state. So here we have these sensors embedded. I don't have a, you can kind of see they come out the butt of the robot and go all the way back. And so these are hooked up. I had some voltage dividers to read them because they were analog sensors, and then those are hooked into a different Arduino that's reading all of those analog signals. So same thing, you have sensor coming the opposite way. Those go into your Arduino packages that, sends it to ROS. ROS has a node that processes it and turns it back into, so this is, did we read 0 or 100% actuation, right? And then that goes back into our RL algorithm as the state. Move this. Okay. And then we have our ground truth acquisition. I'm gonna get some water.
Do you have a time lapse of your learning?
Mm-hmm.
You do? Ah, cool.
I don't have a time lapse of the learning. I have a time lapse of a learned model compared to an unlearned model.
Mhm.
The time-lapse of learning is, Alex, yeah.
You're probably walking around your apartment all day. Yeah.
Dude, it took, some of the sessions were about 20 hours.
Wow.
Yeah. So, so for the ground truth, we use these April tags here. This is just a calibration matrix. But you have this tag here, and we can get X, Y position, and we know where it is in frame. Inexpensive, accurate, tools already exist for it. So like I used a prepackaged camera and April tag ROS package that just kind of took care of it for me. The other thing is I wanted to build this in a scalable way. So you can, April tags, there's up to 32 tags you can identify individually. So you could wrap a big soft robot in a bunch of tags and get a bunch of ground truth data if you were like trying to grab a coffee cup or something with a hand. And then the other is you can have cameras all over the environment and figure out, right? I just needed one and one. I also wasn't smart enough to figure out how to get more tags to work. Thank God I only needed one. I use April tags in my job and I have since figured it out. Okay? So this works the same way going backwards towards the RL algorithm. We have our April tag picked up by the camera. We have an image processing node that determines its position in frame, publishes that to a script that basically, it gives a lot of data, right? I only wanted XY position. So I just pull that XY position out and I publish that for the RL algorithm to understand.
And basically the further it moved along is the reward, like the higher that number is.
Yeah, I'll go into detail about the reward calculation. So this is system control and monitoring. Like I said, I used the coolant pin to determine if an action was complete. Had a little blue LED here that would do that. And I got so sick of a blinking blue light in my apartment. Oh my God. And then, yeah, like I said, I was connected to the Gerbil reset pin. So I think it was like every 15 minutes or so, I would just reset the whole system and rehome it because it just didn't last long enough. And I found a happy medium. So this, what's that?
Is that Windows resetting it?
Oh, yeah. So here we have the coolant pin that's red. Whether or not an action's done, that's fed to the RL algorithm. And then every once in a while, the RL algorithm would say reset the whole system, and it would recalibrate and home the stepper motors, so it knew where it was at. So all that just to get to actually trying to learn. So we have soft robots, we have reinforcement learning, we built the whole system for everything to interact. So now we have the actual robot and the actual learning. So these are a few images of the process of building the robot. It was a 3-part mold. The robot was designed by myself, so it's a novel robot made with 3D printers and silicone molding. So one of the things that's important about that, like I said, the sensors weren't all that accurate. So each robot was manufactured slightly differently. Each robot behaved a little differently. But that doesn't matter because your reinforcement learning algorithm is learning on the actual hardware. So you don't need your robot to be identical. You just need it to learn its own thing.
No two robots are identical.
Yeah, exactly. So we have this here, it's just some pneumatic channels. So you pull this out and you get that molded, and then you turn it over and you do the bottom and you embed the sensors in here. These are the sensors. They have these little 3D printed things that are like literally 2 layers of 3D printing. And then they hold this sensor in and are super glued. And these holes here keep it static in the silicone. So part of what I learned from the home projects is I tried to embed these, but they were sharp and they would cut into the silicone and like make their own like chamber essentially. And then they could move around. So this kept everything normalized. And then on the bottom here, so I had to build a robot that I knew was actually capable of what I wanted it to do. I knew it needed to move across the table. And so initially when I built it, it would go up and then it would relax, but it wouldn't actually move forward. And so I used these scales here to essentially make sure that when the butt slid forward and relaxed, it would push forward the fingers. This was funny. There was a girl that I was dating in grad school.
Oh, boy.
Don't worry. She made her own clothes and like did some Etsy stuff. And then we stopped dating.
This is really funny, actually.
But she had a Cricut, which is like a home CNC knife plotter.
Hmm.
And I called her about 2 months after we stopped dating, and I was like, listen, I won't graduate if I can't use your Cricut. Can I come hang out for a day and just cut a bunch of robot stuff and leave you alone forever? Thankfully, she was very accommodating and let me do it. So I had to go hang out at my ex-girlfriend's house for a little bit. So here's the top of the, this is just a bigger example of the robot.
What'd you cut out? Sorry.
What's that?
Did you cut out those pieces there?
Yeah, these like scales.
Are they
Yeah.
vinyl and you stuck them down like that?
Yeah, they're just like a thin sheet of plastic, but pretty strong. And so you cut this pattern in it, and then you like fold it out and individually fold each one out. And it gives it the scale feature. So it's kind of like a mold.
Like
I got the idea from
Yeah.
skins.
Yeah. Cool.
So yeah, this was the final robot. You have 2 fingers that are able of actuating and pulling forward, and then a butt that makes sure that you move forward. Right? And there's sensors embedded in the bottom and this Able tag on top. If anybody is interested in doing anything like this, there's special epoxy called Silpoxy. Regular glue does not work on silicone very well. And so if you want to do something with silicone, just know that there are special glues out there for it.
What about silicone itself? Are there different blends or is it
There's
just-
different types of silicone, but most of them, like Silpoxy is the way to go. Okay, so here's where we get into some graphs here. And these are tough to explain, but essentially I had to figure out that 0 to 100% region that my robot would actuate in. So what happened was, and I think this one, so this is better. This is very visual. So these millimeters are in terms of how far the syringe would be closed, and therefore how much air would be pumped in. I didn't care about the volume of air. I just cared about its relative to motion. So as you increase, you start to get a little bend here. Keep in mind the end of the sensor is right about here, because as you start to increase more, so 60 millimeters, we kind of have this really nice curve here. And then after that, it kind of bends around the end of the sensor. And you don't move forward anymore, you just inflate this front tip, and then it just moves up. And so from that, I was able to determine through the sensor data that this is when we started to plane off and not actually bend anymore, because we were going around that sensor. So from the beginnings, because if you inflate it with just a little bit of air, nothing happens. So that's not interesting. So from like 18 to 60 millimeters, this was the range of useful motion. And so this was 0 and 100%, right? Cool. And so with this one, your right actuator is I'm sensing and actuating my right actuator. And then my left actuator, this is an interesting problem in control, right? A lot of times in rigid robotics, if you move one joint, you're only moving that joint. However, in a soft system, as I inflated this, you can see that my state of my other one was changing with that.
Do you only inflate one?
So I inflate both at the same time, but this is just calibrating, right? So I was only inflating one here to understand the system, but then I noticed that I was getting different readings based on this one, which means that actuating one actuator changes the state of the other, right? So this is an extremely difficult problem in traditional control development. However, with reinforcement learning,
There you go.
we get all that fuzzy logic. It just starts to learn it and starts to know, right? So although this was an interesting thing and a huge problem if I wasn't doing reinforcement learning, I don't have to care about that. I didn't do anything special to accommodate that. So here's a reminder of the setup, I think. Yeah, it's a workflow example. Okay, so if we're saying the laptop's over here, this would generate an action, pump out through here, it would actuate the syringes, that would inflate these fingers. Your camera here would read how well that actuation moved across the table, take that, pump it back into the laptop as a reward. So this is the whole cycle here.
Nice.
Was that a video or?
No, we'll get there. So this is where the reinforcement learning gets really difficult. And I kind of mentioned it earlier with the amount of parameters that are in there. So your hyperparameters describe your learning algorithm. So some examples of hyperparameters, and I mean some examples, there's a lot more. How many steps do you take in a given what's called episode to populate the neural networks? How many things do you do before you say, I learned something or I want to take information? How long do you delay populating those long-term memory networks? How big is your batch size? So that's like how much information is in that replay buffer that you pick from. How big is that buffer, right? How much information do you put in there? How quickly do you learn, et cetera, et cetera, et cetera. So many things. This is why they were using reinforcement learning to learn how to determine these hyperparameters. And then, so this is one way to tune your learning algorithm, and the other is reward shaping. So calculating a reward is a design decision, right? You don't just say higher reward. You don't just read it and then use that as the reward, right? You really want to push the robot or the AI agent into a certain behavior. And so you give positive rewards for desired behaviors, negative rewards for undesired behaviors, and in my case, modifiers to help specify either desired or undesired rewards. So when it comes to rewards, or some general notes on hyperparameters, right? Can't go into everything. One of the things was that reinforcement learning algorithms are based on a negative 1-to-1 scaling. So instead of 0 to 100%, I had to map everything down to negative 1-to-1, run it through the algorithm, and then pull it out from negative 1-to-1 back to 0 to 100. Fine-tuning the normal or the noise added at the end of, so when you choose an action, you add noise. Fine-tuning that was important. I actually changed that noise over time.
Was it a certain distribution, like white noise, uniform, or?
Oh, it's a normal distribution.
Yeah.
Another is delayed learning start. So this is where you were talking. I took, I think, 2,000 random actions. Maybe my slides will tell me differently. But you take a certain amount of random actions to populate that replay buffer with a bunch of different things, and then you start converging on a behavior that maximizes your reward. Smaller batch size, I don't remember exactly what that means. Increased learning rate for tau and delayed updates. Yeah, I don't know. Anneal noise, that was the big one. So this is fine tuning the standard deviation. So as I learned more, I decreased the amount of noise and kind of accepted the fact that I was on a path to a good solution. So the other is you have a reward. So for positive distance over greater than 0.5 millimeter, I would do 10 times that as the reward. If it did nothing, and I had this huge problem where it would just converge, and basically the best thing it figured out to do is sit there. And I'm like, that's not what I asked you to learn. Like, stop doing that. And then I finally realized I could tell it to stop doing that. So if it didn't move, it was absolutely like a huge negative reward. It was kind of a hack, but it worked. And then for negative distance, right, I don't want it to move backwards. So I just at random chose 2 to multiply it by, and basically
as a negative.
Yeah, if it moved, if it took an action and the tag moved backwards,
Yeah,
that's bad.
It
We
would
don't want
subtract that.
Yeah.
As a reward.
Yeah, your reward would go down.
Yeah, got it. Cool.
So this is what a good learning algorithm. No, this is what I thought was good and then failed learning algorithm looks like. This is attempt 1. So keep in mind, it took about 2.5 months of learning. And like I said, it was 20-hour sessions. So I would turn on my robot. It took about 2 hours on average for it to reach the end of the camera. And so every 2 hours, I would have to go reset my robot. So I would set my alarm at night, 2 hours. I would wake up, tend to my robot, click play, go back to sleep. It's like having a child. Yeah.
It's your baby.
Yeah, exactly. And so here's just a bunch of Hyperparameters that I chose, we don't need to go into the details of that. I think some of the important ones are like learning rate was like 0.003 is the default value. I like bumped that up a lot. Let's see here, trying for good top. Noise standard deviation 0.44. I don't know. So essentially what we have here, so this is okay, it was 1,500 steps. So here we have 1,500 steps of random actions. So we're not doing anything good or bad. And then you can see the learning kick in and you kind of raise up to this thing. And this is how you tell if something has learned, right? That reward climbs and climbs and climbs and then kind of
Is that the
planes out.
reward value on Y?
Yeah, so this is the episode reward value on the Y. One of the things about neural networks is that they're really finicky and they can do what's called crashing. And essentially, that's what happened here. So we learned, and then it crashed. And so the output of this learning section, I couldn't take the model from the middle of this. The output of this learning section was a terrible model, right? Here's some other things that are important to the reinforcement learning community. I don't know. The policy loss they use is another metric of learning. This is essentially like your error, I think.
Yeah.
And so, or your error reduction. And so as this goes up, you get less error. Oh, no. It is your error because it goes down initially, and then when it crashes, it goes back up. So there's, I don't know, I'd have to pull out a book to talk about that. But eventually, I get successful attempt 2. So this one had a standard deviation of 0.44. If I get to step 2, what I figured out is you can anneal the noise. And so as I start learning, every 1,000 steps, I would multiply by a factor of 0.9 and decrease my standard deviation. So I would say, I learned a little bit, let's stop exploring so much. And so here you have about, I think, 1,500 random actions still.
What is a single action? Is it the like one step?
Yeah, so a single action will be a command given to both actuators. So if we started at 0 and it said like left to 10%, right to 50%, that's an action.
And that's one action. And then does it go back to 0?
No. Then it says, okay, I'm in this state. How do I maximize reward from this state? And so then you take another action from that state. And that's why you have to populate so much data.
Yeah.
Right? Because you have to know not only what to do from 0 state, but what to do from every state that the robot can be in.
Right. Okay. Oh, interesting. Wow.
Yeah. And so here we have a bunch of random actions, and then we can see it goes up here and then kind of crashes, goes up, kind of crashes, and then eventually we converge on this spiky graph. I don't know what the spikes are for. My advisor told me to look into it, and I said, I'm ready to graduate.
Do you get to see that live while it's happening?
No, this is
If you're a better programmer, you probably could. But I didn't.
So you're just kind of you're giving it an arbitrary time frame, basically, and saying.
Not a time frame, an action frame.
Oh,
So it took
I see.
8,000 steps is what it would do.
Okay, so you picked 8,000 as the number, or whatever.
Really arbitrarily.
Yeah. Okay. Yeah.
It was a happy compromise of like it would
Your
take
time.
between 15 and 18 to 20 hours.
Yeah. Gotcha.
A very practical choice.
Yeah.
What graphing tool are you using here?
I don't know, the AI tools pump these out. I took a screenshot.
Oh,
Yeah. If I was a better programmer, I would have gone in and grabbed this data and put it into Matplotlib. But I wasn't, and I was ready to graduate. I saw this graph and I was like, oh my God, there's a light at the end of the tunnel.
Like it actually.
It's like I did it. Okay, so this is a learned policy comparison with an unlearned policy. So the metrics here are, you have random actions, you have my learned policy, and then the percentage increase of how effective it was at these things. So first thing is in 1,000 steps, we had a 436% increase in distance traveled. So definitely a better model for moving. And remember, my robot was built to only move forward. So even with random actions, you still traveled some distance, right? And then the same thing with velocity. We had a 270% increase in velocity for 1,000 steps. So yeah. So on the left, you have your learned policy, and on the right, you have your random policy. And so you can kind of see, it's interesting. So random obviously is just doing whatever it wants. But this learned policy, if you notice, it kind of turned to the side and then used one leg to kind of drag further, figured out that one leg was better than the other. I really thought it would just move forward. Like I thought I designed a robot to do something good. But
Some mechanical difference.
Yeah. could be
Yeah.
that too.
yeah, and that has to do with the manufacturing inaccuracies.
Mhm.
Sometimes the pneumatics work. So like,
That's really cool.
yeah. So some of these tabs would actually basically soak up more inflation than the others. And so like one, it may be the third tab, which would change how it actuates. And the other, it may be the second tab, which would change how
But
it actuates.
inconsistently.
Inconsistently.
Yeah.
Yeah. I couldn't manufacture them accurately enough for it
Right.
to be deterministic.
But if you made your ground truth just orientation with the April tag, like you just wanted X and Y, but if you made it, theta.
Yeah, I
then
could
it
train
might-
it to
it
stay
would
straight.
learn- Yeah.
Yeah, if I added a reward signal to maintain straight, it would learn to move straight. I was more interested in just how would it figure out how to move
Right,
across
yeah.
the table.
That's cool.
Super cool.
Yeah, and so you'll see here, I think in random policy, it gets really dim, and that's when I started playing it. At some point, there it is.
Now, does air versus like water versus air in as your fluid? Doesn't really matter.
I don't know, I didn't build a water-based
Yeah.
robot. Yeah. Beer-based robot, that's water and air.
Oh, yeah.
It's a good hybrid technology.
Dang, that's so cool.
Yeah. Oh, this is great.
So I did an afternoon of investigation into the spikes.
What's successful?
This is successful learning attempt. So this is the reward
Successful.
process.
Can I see it?
Oh, successful. It's, well, I mean, truly, it's suspiciously successful.
You did pass. So
Yeah, please don't read my thesis. There are so many like error references not found in the actual published thesis.
You're a real engineer.
So what I did here is I had different regions of the camera, and I just moved the April tag into different regions and like compared the two to see if the readings were like somewhat accurate. Really, I just did this to satisfy my advisor and give more numbers. I didn't care. I don't know. It learned whatever. So yeah, future work, fully automated testing, so I don't have to wake up every 2 hours. Maybe something that can like put it on a conveyor belt, and the conveyor belt moves the robot back, and you have this environment that moves with it. Develop an understanding of RL hyperparameters and reward shaping. That is an active area of research, and there's millions of dollars of funding in that. Extend April tag support, basically be smarter and better at programming. More automated calibration and characterization. So that's more as a tool of like you build a robot, like make better tools to understand how that robot behaves before you put it into the RL algorithm. Extended sensor support. I had one type of sensor, an analog sensor. I mean, it's an Arduino pumping things into ROS. So you could do I2C, you could do any type of sensor that can plug into an Arduino, you can pull that data off. Additional actuator types. So like I mentioned, it's an active area of research. There are tons of different ways to actuate soft robots. I chose one that was cheap and simple. And there was a lot of focus after COVID. We kind of realized it was a blessing too, because now, I did this for less than $500.
Wow.
Right. The computer was a computer, but all the equipment and stuff, the table, I did it on equipment for less than $500. An improved syringe actuator. So each one of those was bought off of Amazon. They were like 99 cents a piece. You could get a real one, but I proved that you can do it with the crappy ones, which is pretty cool, I think. And then user interface improvements, live plotting of relevant data, live April tag overlay on the video stream to know where it is in frame and kind of show data as you're doing it. I made this for myself, and it worked for myself as someone who was learning Linux, ROS, detail programming along the way. Like yeah, if I could go back, you could do a lot of cool things.
And
Damn.
it was cool.
Well, what was your grade on your thesis?
I'm here. I got a degree.
No, no.
There is
okay.
there is no grade. It's a binary.
Oh, is it?
Yeah.
Is it? Oh, okay.
You pass or not.
Ah.
And so to put it in context, I was actually a little frustrated because my professor was like, dude, you're like one chapter away from a PhD.
Yeah, I mean,
Yeah,
definitely.
It's I didn't realize how ambitious I was at the time or how complicated this would be.
What was the time frame
I started my research in earnest. So first of all, I had an 8-month internship understanding soft robots and building soft robots. I took that to my advisor and said, like, here's a thesis on a silver platter. It's with NASA. And he was like, yeah, let's do it. So it was like probably March or April that I started in earnest building. And that was when I got back from COVID.
Wow.
I got stuck at home in Kansas City with COVID. Not with COVID, but COVID hit when I was home in Kansas City. So I finally made my way back in about April. And then I started in earnest, and it was like solid, it was October after that. So 6 months of being in my apartment, waking up, doing robot stuff, going to bed. And like, I couldn't do anything else, right? So yeah, it was just like 6 months of probably 12 to 16-hour days.
That's awesome.
With a few like, oh, thank you.
Wait, I have one more question. What are Asimov's 3 laws of robotics?
Don't harm humans. Oh shoot. Don't harm
yourself.
humans. You can't. They must obey unless it violates the first law. Don't harm humans, and then it must self-preserve unless it violates the first 2 laws.
Bravo. Look at that.
Yeah, you're fast.
Thank you. I didn't Google that before this talk.
That's awesome. No, thank you, man.
That
This
is
is awesome.
so cool.
This is PhD. I mean, this is.
Oh, yeah.
Yeah, so I had a friend who sent me her master's thesis when I was started to write as an example, and hers was like 20 pages. It was like a research paper, and mine ended up being 9 pages or 90 pages.
90, yeah.
Yeah, with like 70 something references.
Oh my god.
Yeah,
I mean, you tackle a lot of hard problems
A
individually.
lot of pieces for that.
yeah. Didn't realize it at the time.
Great work.
That's awesome.
So thank you, internet. I don't know if we can. Are there any questions? Is there like a chat? I mean, we hardly figured out how to turn it on. So.
I bet. Oh, no.
I see one person.
Yeah. Yeah, I don't know, actually.
Does it say the name? Who's the one person?
It's just bubble.
Oh, nice. Probably my mom.
Oh, wait, end stream.
Whoops.
Okay. Well, end it.
End it?
Yeah.
Okay.
Yeah.
And then
Bye,
I'll-
everyone.
Bye.
I'll post this.
Yeah.
So-
Damn, I just realized it's